I am Glorie May, presenting on behalf of Stephen John Destura, Audie Cabrera, and Jhoanna Rhodette Pedrasa. This short paper entitled Wireless Sensor Network for Telerehabilitation of Parkinson's Disease Using Rhythmic Auditory Stimulation. Parkinson's disease is one of the most common neurodegenerative diseases in the world. It mainly affects the elderly population and has a mean age diagnosis of 70.5 years. Symptoms for this disease include difficulty in speaking, impaired posture and balance, resting tremors, and shuffling slow and short steps. It is a progressive disease and usually gets worse over time. Currently, it does not have a known cure, and patients undergo physical therapy in order to manage their condition. Physical therapy is one of the ways to manage this disease. Its goal is to engage patients in exercises geared towards improving physical capacity and functional mobility to improve their quality of life. Patients are encouraged to engage in physical therapy for at least 6 months to achieve clinically meaningful results. Rhythmic auditory stimulation is usually incorporated in the therapy of the patients. It involves the use of auditory cues such as music and rhythm, usually with the use of metronomes, in improving the motor functions of patients. While some studies show that RAS is effective, a recent study in 2021 showed lower uptake of RAS for telerehabilitation. Considerations in the patient's conditions must be addressed in the remote setup, including safety, access to a caregiver, and technological challenges. One emerging form of physical therapy relevant in this COVID-19 pandemic is telerehabilitation. It is the use of technology to deliver evaluation, consultation, assessment, and therapy to patients through the use of information and communication technology. Telerehabilitation can be asynchronous through the use of messaging applications, and it can be synchronous through the use of video conferencing applications. However, both of these methods can prove to be unreliable, since they only provide subjective assessment of the patients. Thus, developing technologies to assist in the telerehabilitation is beneficial in providing convenience for those in remote places, in saving time and money for transportation, and in social distancing due to COVID-19. There is a need to develop a system that can give objective assessment for monitoring the rehabilitation progress of Parkinson's disease patients at their own home. The possible impact of this study is, first, it can give guided self-management and individualized treatment plans. It can also help them save time and money that they could use for transportation. Given the COVID-19 situation, it can also help in social distancing and in limiting the time spent outside. Lastly, it can ease the supervision of the therapist for home-prescribed exercise programs by objectively assessing and monitoring patients' progress. Here's the system overview. Each patient is considered as different sensor nodes. Each sensor node has its own base station node, which connect to the cloud server. Looking at the in-depth overview of the system, sensors are placed inside the footwear of the patient. It is wired and controlled by the control box, clipped around the waist of the user. The microcontroller on the control box is connected wirelessly to an Android phone using Bluetooth connection. The phone will upload data to the cloud server using Wi-Fi connection, and the therapist can then access and view these data from all of their patients for assessment. At the same time, patients can also view their own individual training data. So now, let's go through each part of the system. The component designs were validated through our consultant physical therapist. Firstly, the sensor node has two main components, the microcontroller module and the insole sensors. The insole sensors are placed inside slides and worn by the patient. It is wired directly to the microcontroller. The microcontroller is housed inside a control box, clipped on the waistband of the patient, along with the necessary circuitries. Velcros were used to strap the wires connecting the insole sensors to the microcontroller to prevent obstruction during training sessions. Rubber shoe insoles were placed on top of the sensors before installing in the shoe to add a layer of protection. Pucks made from rubber foam materials were placed on top of the sensors, used to ensure even load distribution and better load detection. And footwears with open backs were used so that the tail of the sensor can pass through to prevent bending and stress during training. Next is the microcontroller module. Arduino Nano was chosen because of its small size. It is responsible for computing data gathered by the insole sensors. It is also responsible for sending the computed data to the base station node through Bluetooth and using a Bluetooth module HC06. A 9-volt battery was used as the power supply of the system. These were placed inside a casing strapped around the waistband of the user. The microcontroller calculates different step parameters, including the total number of steps, the total correct steps, and cadence, which is the total steps per minute. For correct steps and total steps, minimum trigger point must be achieved, and stepping duration must also be achieved. The correct steps are defined as steps initiated within the duration of the beat. It measures how much the patient was able to follow and keep up with the beat prescribed by the therapist. The training parameters are the beat frequency options, 49, 55, and 60 BPM, and the training duration, 10, 15, and 20 minutes, which are used in the application and recommended by the therapist per training session. For the patient's side, the main function of the app is to facilitate RAS training sessions by playing the beats. Patient side features include viewing past training results, viewing schedule, and starting the training. Each training session uploads computed training parameters, such as total steps, correct steps, and cadence, into the database and is viewed as a line graph in the application for easier viewing. On the other hand, the therapist can monitor and assess their patient's training programs using the features Select Patient, View Schedule of Training Sessions, View Past Training Sessions of each patient, and provide training feedback per training session. Lastly, the server. The application is connected to the server to obtain data through Wi-Fi. It is a cloud-based implementation to store a database of patients' data, such as user information and training information. Firebase was used for the cloud server as a database and authentication for users. Testing was done on each of the system's components: sensor node, base station, server, and the full integrated system. The first test done was the no-load test. Which checks if the system detects any stray and unwanted signals when no load is applied to the sensors. For 3 10-minute no-load tests, an accuracy of 100% was obtained. no stray signals were generated with the filtering. Testing with load was conducted first with different known weights of 1 kilogram increments on the FSR cell, and its corresponding value is read through the Arduino serial monitor. The trigger point was found to be 2 kilograms. The correct step and total step tests also utilized the load testing. Filtering was done to implement the minimum step duration for the total step counter in the code. A step must be held for a specified amount of time in order for it to be counted. These durations per BPM are noted in the table. Off-synchronization of the microcontroller and the phone application was evident. A noticeable delay of 536 milliseconds between the time the audio starts playing and the time the start command is received by the Arduino. This off-synchronization greatly affects the performance of the system for longer durations, since delays accumulate. Synchronization is critical since phone and microcontroller generate beats independently. Moreover, since correct step conditions do not depend on total step conditions, any direct calculations between the two parameters, such as the wrong step, is not possible. Data sending and receiving on Bluetooth and Android app were tested using Bluetooth serial application and the Arduino serial monitor. Moreover, off-synchronization was resolved by waiting 536 milliseconds before playing audio on the phone, allowing Arduino to receive data and generate beats. Tests on the Android application involved user interface testing to validate component interactions, and database testing to validate uploading and query, and simulated training sessions to check the application's capability to facilitate training sessions. Server was used for database and authentication. Testing involved uploading dummy data based on the setup field on the database. Information included user information, training schedule, and step parameters. The full system functionality was tested with training sessions varying in BPM and duration to ensure every setting was working. Application functionalities for different user roles were also checked. The system's capability to handle multiple users were simulated to ensure that data sent in the database corresponds to each user properly. 3 patients to 1 therapist account was used, with the therapist being the only account that can view all patients' data, while individual accounts can access their own data. In conclusion, a wireless sensor network was designed and implemented to aid Parkinson's disease patients and therapists to objectively assess and monitor rehabilitation progress during telerehabilitation. Considering the age demographic of the users, ease of use and comfortability were considered in the design, which was approved by the consultant physical therapist. The system is composed of a sensor node, which gathers step parameters, a base station node in the form of a phone application, which facilitates training, and a server, which serves as an online authentication and database, which provides therapists access to patient data. The system has an accuracy of at least 80% and 70% for the total step and correct step parameters for the 10-minute duration, respectively, which are acceptable values given that the system is in its first stage of prototype development. Thank you.